Yeah, hello everyone. Thank you very much for giving me the opportunity to present to you some of the work that I've been doing in the past couple of years or so, and it's good for me to be back to geodetic, at least virtually. Who knows? Maybe at some point we'll be able to travel back again, and so I might be able to see you in person at some point. So anyway, today what I'm going to present is the work that I've been doing on the Iquique earthquake, which is an earthquake that occurs in Chile in 2014. And what I'm most interested in this earthquake is the nucleation phase, because it was quite studied and debated on what was happening before the occurrence of the main shock. And in particular, what I'm going to attempt to do today is to get some estimate about the seismic and aseismic slip partitioning before this earthquake, because it was kind of a part of the debate that was going on when this earthquake happened. So I'm going to start with a very general and broad introduction. And the main question that underlines this work is to basically understand how earthquake starts. And the more specific question behind it is to know whether we can detect the nucleation phase of an earthquake. And what we know very generally is that during what we call the interseismic phase, you have a fault that is progressively accumulating stress at rather low velocity, on the order of some millimeters per year. And at some point, that fault cannot hold the stress that is accumulated, and it breaks into an earthquake. And the stress that has been accumulated suddenly released pretty fast as well, on the order of meter per second. And one of the main questions is whether this transition from a locked fault to an earthquake, is it happening like suddenly? There is no warning or no preparation phase whatsoever, or is there something that can inform us eventually about the fact that an earthquake is going to happen? And from lab experiment, from observation in nature, and from work, theoretical work, it's been quite suggested quite a few times that there is actually some sort of a preparation phase before an earthquake. And this led to proposing two sort of conceptual model of how earthquake starts. So here is some sketch about what we think are the two end members model. This is a figure that I took from a paper by Carl Tepp that went out in Nature Geoscience in 2018. And so you have those two type of model, what's called the slow slip model and what's called the cascade model. I'm going to now explain a little bit to you what are the specifics of this different type of model. The first one here is the cascade model, and there's one relatively famous example of this type of nucleation phase, and it's the case of the aseismic earthquake. And basically, the idea of the cascade model is that you have one rather small earthquake that is triggering short-term or long-term another rather small earthquake, and so on and so on and so on, relatively close to the future main shock. And at some point, one of these earthquakes is really going to grow and become what we think is the main shock. This is an apparent stochastic process. I'm saying apparent because there might be some underlying mechanism, but that might help us to eventually predict this cascade failure. But let's say at the moment, we don't know too much about that. And so it seems to be rather a stochastic process. And yeah, the example, for example, of the aseismic earthquake is highlighted here. This is a paper by Lethworth and co-author. And what they show is that you had do you see my mouse, or do I point in the shadow?
Yes, we can see your mouse.
Yeah, so basically what happened in this earthquake is that you had the first one that changed the state of stress on the fault, that triggers another one, and so on, until you have the occurrence of the main shock. And so that's one end member of how eventually you go from the interseismic phase to the coseismic phase. And another model that has been proposed and that has very large evidence from laboratory experiment, it's what's called the slow slip model. So this is a rather different process in the sense that here you have a rather progressive acceleration of slip on the fall. So you start from one place and there is a patch of slip that is progressively growing and progressively accelerating. While it does that, it also triggers some seismicity, which we will call foreshocks. And this slow process is aseismic in general, meaning that the velocity at which the fault is slipping is rather low in this case. And as I was saying, there is quite a few evidence from laboratory experiment. This is one by Soumaya in Toulouse, in which you can see as time goes, so time is going up in that direction. As time goes, you have a progressive acceleration of the slip on the fault, and this is during what's called the nucleation phase. And at some point, you reach a critical speed and you start slipping at coseismic slip rates, and so you start triggering your main shock. The idea with this one is that because it's a rather slow process, and it might be more deterministic in some way than the cascade model, even though this is still a question to debate. So just to summarize these two conceptual models, so you have the slow slip model. So again, a patch of slow slip progressively accelerating. And what is interesting with it is that it leads to a potentially forecastable earthquake eventually. And on the other hand, you have the cascade model in which earthquakes are randomly triggering one another, and then it's more difficult to forecast eventually. And so you have example in nature of these two types of end-member models, but there was one earthquake in particular that kind of crystallized the whole debate about whether earthquakes start as slow slip or whether earthquakes start at cascades. And this earthquake is the Iquique earthquake that occurs in Chile in 2014 in the northern part of Chile. So this is the region of the Iquique earthquake. So here I'm showing the slip distribution that was obtained by Zachary in some previous work in 2015. And what was interesting in that earthquake is that it broke what was think of a seismic gap in the past. So that was one of the interesting aspects of this earthquake. But what was even more interesting is what we could see on the geodetic network before the earthquake. And so what do we actually observe? Well, when you look at the station, and this is a study that is taken from Anne Soke, that she did that looking at the GPS station the coast of Chile, and she basically processed the geodetic data for quite a long time. So here from 2012 to 2014, so just before the earthquake. And basically she color-coded all of the time series in terms of velocity, or like a rate of change of the displacement at the surface. And what you can see is between, let's say, 2010 to 2013, there was pretty much nothing going on. Eventually, some fluctuation that might be because of many different type of reasons. But what was more interesting is that when you look at the final stage, you could see that the GPS data close to the future main shock will really start to accelerate and showing some increasing displacement at the surface that was going faster and faster as time goes. And this process eventually could be traced back 8 months before the main shock approximately. But most importantly, the main signal was really seen, let's say, a month or so before the earthquake. So at the time when the earthquake occurs, so she did that in 2017, but at the time when the earthquake occurs, some people saw that signal already, and they interpreted it in a very different way, and which is why we have decided to analyze this earthquake, because some proposed that it was kind of a slow slip model, and some proposed that it was kind of a cascade model. So for example, a group at ENS led by Sergio Ruiz, they looked at the GPS data and they started to model that nucleation phase. And the way they interpret their model is that it's basically a slow slip event. So there were aseismic slip on the fault plane, some foreshocks were triggered, but most of the slip that happening is aseismic. So we are in the case of the slow slip model. And so on the other end, there was pretty much at the same time another group in Germany from the KFZ laboratory that came up with a very different explanation. So when they look at the GPS signal at the surface, what they show is that basically all of the surface displacement that you observe before the earthquake can be pretty much explained by the seismicity. So when an earthquake occurs, obviously it changed the surface displacement. And when you accumulate all of the foreshocks together, you could eventually explain what was happening at the surface. So in that case, they didn't involve some aseismic slip on the fault. They say that the nucleation phase is pretty much only seismic. So in that case, you might be more in the side of the cascade model. They changed a little bit their discussion. Recently, they published another paper in 2017 saying that there is some aseismic slip, but it's more after slip from the foreshocks than rather aseismic slip from a nucleation phase. But we'll come to that back later. And then there were obviously other people that propose that it's a mix between slow slip and aseismic slip and between seismic slip on the fault interface. And this was proposed, for instance, by a study from Cato in 2016, where he say basically that what we observe at the surface is kind of a mix, an equal mix actually, of fast slip from the foreshocks and slow slip driving eventually these foreshocks. So you can see that this earthquake really, well, first of all, you can see that it has an observable preparation phase, but that the way you interpret this preparation phase really depends on the groups. And so this is why we decided to kind of revisit this example and to see whether we could come up with some estimate of the seismic aseismic slip partitioning using a Bayesian framework, so that we can get access and give some estimation of the uncertainty on that partitioning. And so before doing that, we have developed a scheme for doing time-dependent slip inversion. So usually the way the slip imagery is done with geodetic data is that you take a static image at a given time. But here we also wanted to see not only the spatial distribution of slip, but we also wanted to see how slip evolve in space, but also in time. So we had to develop this time-dependent slip inversion. And so I'll come to the method a little bit later, but let's first start by the observation that we are going to use in our study. So we had access to 23 stations. They are highlighted here by the red triangle. This is just a map of the co-seismic slip distribution from the main shock that was obtained by Zach in this study. So the hypocenter of the main shock is here with the focal mechanism. That is this one, plate interface event. And so we had 23 stations that we had access to. They are coming from different type of networks, so CSN, EFZ, CNRS, and Caltech. So the processing of the data was mostly carried by Emily Klein at ENS. So without going too much into the detail, and she's the expert on that, so she can probably answer your question if you had some. But the raw data were processed using a double difference approach, using the Gamut blockade software that allow us to obtain the relative position of the station between them. And then there was an Helmert transformation so that the solution are expressed into the ETRF 2014 geocentric reference frame that was done using a PIAX that Jean-Mathieu and you guys are probably very familiar with. And then the solution were projected onto the WGS 84 ellipsoid. So that allows us to have our raw data, let's say. So, and then we did some post-processing. So that was done by Paul Rebishung from IGN. And so what he did was a relatively standard approach for the correction. He took all of the time series and he fitted a simple model that is composed of linear functions, which are supposed to model the seismic trends, annual and semi-annual sine function to model the seasonal trends, and some exponential function, so that it models the seismic trends. And once you adjust this model, basically you remove the seasonal component, because this is the things that we are not so interested in. So that way we obtain our time series that we are going to use in our study. But as you probably know, what the time series record at the surface is doesn't care whether the slip on the fault is seismic or whether the slip on the fault is aseismic. So we had to find a way to basically separate the two components so that we can get some sort of an idea of what is the partitioning during this earthquake. And so for that, we developed some sort of a method, or actually I should say Emmanuel Caballero, like a PhD in our group. He worked on a method so that we can correct the time series from the contribution of the seismicity, so that at the end we could extract eventually the aseismic component. And the way we do that is relatively simple. You have a catalog of focal mechanism. In fact, the one that we are using was obtained by Cheska in 2017, and it includes all of the earthquake with magnitude greater than 4.0. And then you take this catalog, and for each earthquake, you produce random realization of the focal mechanism, random realization of the location, and random realization of the magnitude of that earthquake, assuming that we have a Gaussian error. And here are the range that we are using for doing our random realization. And then for each of these realizations, you compute what is the contribution of that at the surface. And so you obtain all of those basically gray line, which are all of the contribution at the surface from all of we're using something like 10,000 realizations. So for all of this realization, you have one prediction. And so you end up with the families of prediction. And then you can compute the mean of that prediction along with this uncertainty. So the mean is the red line, which is shown here. And the uncertainty on the prediction is basically the range given by the gray line. And then you can remove that to the time series. So before, our GPS time series was the blue dots. So you could see that at some point you started to really see something going on that station. So that station is Pisagua, which is a little bit offshore of the main shock. And on that station, then you can remove the seismic contribution from the foreshocks, and you end up with the orange time series, which is shown here. So you can see that there is still some signal at this station that something is going on, but we have removed the contribution from the main earthquakes. So that way we end up with somehow two types of time series. One, what we call original time series. So basically that records seismic and aseismic slip on the fault. And we also have corrected time series for which we hopefully have corrected all of the seismic contribution. And so this one is supposedly reflecting only a seismic slip on the fault. And so then what we're going to do is to use this data and invert for the spatiotemporal evolution of slip. And then by making the comparison between the two types of model, we are able to do the aseismic seismic slip partitioning estimation. So how do we obtain the spatiotemporal evolution of slip? Well, first of all, let me describe a little bit the geometry of the problem. We take a rather realistic fault plane or fault interface, I should say, because we mesh the SLAB 2.0 model. The mesh is shown here by these dots and these triangles. So we have about 27 nodes for the mesh, and the model parameters will be inferred at the node. We are making one assumption, which is that the fact that the slip is going to be aligned along the plate convergence vector. So we have only one slip direction, which is roughly speaking into that direction. For calculating the green function, which is basically the response at a given station from slip on default, we're using the CSH package, which is developed by Romain Jolivet. And it's basically, without going again too much into the detail, but it allows us to use a multi-layered medium rather than a homogeneous medium. And we used a medium that was obtained by Hussein et al. from a tomography of the region. And then the most important part is how do we model the time evolution? Because again, as I was saying, a lot of the methodology that are developed to study geodetic data are using static images. And so we had to develop some sort of multi-window parameterization so that we can include the time component into our model. So the multi-time window parameterization is something that is well known from seismologists because it's been used quite a few years now to study earthquake rupture process. And the idea is that the evolution at a given place, or the time evolution at a given node, is basically the sum of some basis functions that are going to be scaled. And basically, what we are looking for in our problem is the scaling factor of this basis function. So in terms of what do we choose as basis function, that is quite a big choice to make. We haven't tested much basis function, but the one what we are using are called the E-spline functions. So here are the E-spline functions that we are using. We're using 17 of them, one starting every 2 days. And so basically E-spline functions are quite convenient because they are monotone function. They also integrate to one, so they're really suited for this type of problem. And so then what you're trying to do is to find the scaling of each of these basis functions. So then you obtain those dashed lines, for example. And when you sum them all together, then you obtain the temporal evolution of the slip at the given node, which is shown here by the red curve. So that's the idea. So in terms of the size of the problem, so as we have 27 nodes for the spatial distribution of the parameters, and that each node is composed of 17 of these basis functions. Basically, the overall problem is a little less than 500 parameters to find. So that gives you a little bit of an idea of the size of the problem. So now, let's also talk a little bit about the Bayesian sampling. So in order to find, let's say, the value that these parameters or that this scaling should take, we're using Bayesian sampling. And Bayesian sampling have this advantage is that instead of giving us just one, let's say, optimal model or one best model, it gives us an ensemble of model, ensemble that we call the posterior PDF. And this is what we aim to obtain. And from Bayes theorem, it's this posterior PDF can be expressed as the likelihood times the prior PDF. So what is the likelihood? The likelihood is simply a way to say how well a given model explains our observation. So we are using for that a simple L2 norm. So this is the formula that some of you might be quite familiar with. And then we had to choose also some prior. Prior is basically some information about what we think we know about the model. And in terms of prior, what we have tested quite a few of them, and roughly speaking, it doesn't affect too much the solution that we find at the end, but I can talk about that a little later during the question if you want. But what we choose instead is a Laplacian prior. So Laplacian prior, why? It's mostly because it induces sparsity in the problem, meaning that the coefficient or the scaling factor are going to be only non-zero when the to be non-zero. So that's why we use this type of distribution rather than, for example, uniform or Gaussian distribution. And then just a little note on how this big problem is solved. We didn't write our own code. We took the one that was developed mostly at Caltech, and it's what is called Altar. There is now a new version of that code that can be actually found here if you are interested in. And it's kind of an adaptation of the cascade adaptative tempered metropolis in parallel algorithm, or CATMIP for people for like shortening the name a little bit. That was developed by Sarah Minson in 2013. So that Altar is basically solving that problem, and so that we start from the prior and we progressively reach the posterior PDF. And so that's basically the setup of the problem that we are going to solve. And so now let's come to the results that we have. And I'm going to start by showing you the spatial pattern of preslip. So I'm only showing you, and I'll show you some snapshots after that. But now this is basically the cumulative slip just on the day before the main earthquake. And this is using the full geodetic signal. So the signal that basically is not corrected from the foreshocks. So it records both seismic and aseismic slip in some sense. And this is the median model that I'm showing you here. And what you can see is that is a relatively simple model, nothing very fancy about it. So you have one main patches that is here. It has a peak slip of 10 centimeters, 11 centimeters, plus or minus 0.4. You can see when you look at the PDF, for example, of that portion of the fall that is rather well constrained. Because the PDF is relatively narrow. In order to get a slight better vision of what is the uncertainty on the whole fault plane, what we compute is the coefficient of variation. It's a fancy name for saying that is basically the standard deviation divided by the model, so that basically it reflects how big is the standard deviation with respect to slip. So for example, here you have a rather large slip of 10 centimeters, and you have a very low standard deviation. Here you have a very low slip, but very high standard deviation. So meaning that this point, for example, is less well constrained than this point here. But what is more important is that where we have a lot of slip, basically we see that the uncertainty is rather low, and so that this portion of the fault is rather well constrained. So that is for the spatial distribution of slip. But how does it evolve with time? Again, it's rather hard to show because we have an ensemble of models. So instead of showing you, let's say, various models, what I'm showing you is the temporal evolution integrated over the whole fault plane and expressed in terms of moment rate, so Newton meters per day. So not cumulative moment, but moment rate instead. And what you can see is that what we find is that there is rather three phase, that we observe. The first one is this one that lasts for about 10 days or so, and in which the moment rates do start to accelerate a little bit, but not so much. And there is no earthquake occurring during this phase. When you start to reach phase number 2, you start to have this very large increase in moment rate, which peaks here about 15 days before the main shock. And this happens to be at the same time when we see that we have a lot of earthquake. So that the number of earthquake is shown by the blue bars. And so you can see that at the time when you start to have this really large increase of moment rate, you also have a lot of earthquake happening on the fault plane. And this swarm, let's say, of earthquake do last for quite a while. And so this signature that we have here from the seismic sequence remains relatively visible for, let's say, 10 days as well. And then during the last few days, we do have some earthquake, but not so much. But what we see is that we start having this acceleration phase again. And so we do have some sort of nucleation phase in which you start here and then you progressively accelerate here. But then at some point you have the seismic sequence that is starting to blur a little bit the vision that we have on what is happening here. And this is can be also seen to look at the temporal evolution of pre-slip. So these are different snapshots of the slip rate on the fault, along with the focal mechanism that we have from our catalog. And as you can see here is that, let's say 27 days to 18 days before the main shock, nothing much before the main shock, we start to have some slip rates. So the slip rate here is starting to accelerate a little bit. And then you have a strong correlation between where the slip rate is occurring and where the foreshocks are, which are shown here by this by the focal mechanism. And then the slip rate is slightly decreasing a little bit, 3 days, and then it starts to accelerate a little more at the end of the process, maybe before the main shock. So this is what we obtain when we use the full time series. Now, what do we obtain when we correct for the signature of foreshocks? Well, when we do that, we obtain a model that is to the first order not so different from what we have obtained before. The main difference being the slip amplitude that we have. So, for example, this is now the spatial distribution for the median model. And what you can see is that you still do see that blob of large slip that is happening here, but instead of being 10 centimeters as it was before, it's now only 3 centimeters on the fault plane. Again, this is the slip that is just on the day before the earthquake. You can see that you have also a little background slip, which is rather which is, let's say, because of the amplitude that is less and the uncertainty on the data that is larger. But again, in terms of uncertainty, if you look again at the uncertainty over the whole fault plane by looking at this coefficient of variation, what you see is that where you have the main region of slip is rather well constrained. The standard deviation is low with respect to the slip amplitude. And places, obviously, where you have zero slip are rather uncertain, but they contribute less to the fit to the data. In terms of the temporal evolution, now we see is that we still do have these 3 phases that I was describing before. One, first acceleration here that we see. Then we still seems to have a remaining signature for the from the foreshocks. There is some question, and I'll try to answer it at the very end of this talk, whether this is afterslip or missing foreshocks. We are more in the range that it is very likely or quite likely to be afterslip. And then at the very end, you do start to see that increase. That is, instead, before it was kind of blur because of that big bump from the foreshocks, and now you can clearly see that at the end there is quite a large acceleration of slip rate on the fault. Same thing when you look at the temporal evolution, you can see that it's not so different, but it, instead of being like a very nice correlation of the foreshocks and the slip on the fault, instead what we see is that the foreshocks seems to be kind of surrounding the region of main pre-slip instead of being just following the pre-slip that we find. And again, we have a kind of a peak around that time, so like 15 days up to 6 days, and then it slowed down a little bit before reaccelerating at the very end. So this is what we obtain in terms of spatiotemporal evolution of pre-slip. So now we have 2 types of model. One model in which we kind of records the combined contribution of seismic and aseismic slip, and one model in which we have hopefully only aseismic slip. And so then we can compare the 2 types of model to provide some sort of estimate of what is the seismic slip partitioning on that model. So basically, this is the evolution with time of the fraction of seismic slip. So basically, it's the ratio between the aseismic model and the seismic model over time. We do see again that that 3 phases that we have observed before. at the very start, 1 month before the earthquake, we see that basically all of it seems to be rather aseismic slip, but the moment, as you could see, for example, if I go back a little bit, what's happening before, it's very little anyway. So there is a large uncertainty here, and the moment rate is very small. So it's hard to say whether this is really happening or whether this is just, let's say, noise from the data, for example. And then what you can see is that you start to increase quite significantly the seismic contribution. And in this time period, between, let's say, 18 days to 5 days before the main shock, the fraction of seismic slip is rather significant, because you have about 60% of the slip that is happening on the fall that seems to be seismic, and only 40% that seems to be aseismic. And then you reach the final stage in which things starts to be rather aseismic again, with not much contribution from the foreshocks. And so what do we observe then in terms of the time evolution of aseismic slip? So when you look at the overall fall, this is again what you observe. You observe like this nice time evolution in which you progressively accelerate until you reach the main shock here. And this is just again the averaging the slip rate over the whole node. So this seems to be rather well-known nucleation phase. And so in order just to show that, we took some expression of the nucleation phase that was proposed, for example, by Jean-Paul in his paper in 2008. This is some sort of a formula that describes how slip rate evolve as a function on time with respect to some rate and state parameters. And when we try to fit that curve with the Metropolis algorithm with that formula, we do obtain a rather good fit, at least for the very end part. There is some mismatch here and here, but here it's probably, again, as I was saying, maybe signature from some foreshocks that are not well corrected, or eventually a seismic slip. But overall, we see that at the very last stage, we do observe that nice increase of a seismic slip that seems to be consistent with what we believe from nucleation phase of earthquake in a slow slip model. But again, the question is, what is happening here in particular? And when we focus, so that's when we look at the overall fault. But when we focus on for example, so I'm just going to go back a little bit. Here, for example, when we focus only on these 2 points, so the 2 points that are showing the largest slip, pre-slip. So now when we focus on those 2 nodes, this is what we obtain as the time evolution. Yeah, we obtain this type of evolution. So we have basically a small acceleration of slip at the very beginning, and then there is a sudden acceleration of the slip rate before it decays. And then at the very last few days before the main shock, you do see that increase of slip rate again. And that type of curve is rather characteristic of afterslip. So this is when the largest foreshocks occurred, and you can see that the peak, you have some sort of a perturbation on the slip rate. So you have a very sudden increase of slip rate because of the foreshocks, and then a rather long-term decay of that slip rate. And this is kind of characteristic with what we observe from afterslips, in which when you have a perturbation, then you increase the slip rate at some point, and then it decays until it goes back to plate velocity. While this is kind of resemble a little bit what we see. So overall, when you look at some specific portion of the fall, it seems that a strong influence of afterslip, but overall, the fall seems to be also there's kind of an underlying nucleation phase from a slow slip model. So this kind of ends up the talks. Just a few points of conclusion. One of the things that we have done here is developed a full time dependent slip inversion scheme coupled with Bayesian sampling, so that we can estimate the spatiotemporal evolution of slip on the fall along with its uncertainty. We did analyze the seismic aseismic slip partitioning during that preparation phase. And one of the conclusions that we reach is, at least at some point, about 60% of the slip seems to be rather seismic, while 40% seems to be more aseismic. So this kind of favored the mix between seismic and aseismic slip that, for example, Cato has proposed, and it is in the rather same range of value. And when we look at the aseismic portion only, what we think we see is that we have this long-term nucleation phase that resembles Onaka's style of nucleation, but it is kind of perturbed, let's say, or it is blurred a little bit by some short-term afterslips from the foreshock. That was also something that was proposed by Bedford when they reanalyzed that nucleation. So with that, I'll end and I'll take any question, and thanks for your attention.